Hello, welcome to our first video on projectile motion for grade 12 physics. Over the next series of videos, we'll take a look at projectile motion starting from a simple dropping case to a more complicated launch from different heights with all sorts of different things involved in it. So starting off, the idea behind projectile motion is this is motion that happens when a projectile is given an initial velocity and allowed to fly free under the influence of only gravity. In grade 12 projectile motion, we're not going to consider friction, we're not going to consider air resistance, we're only going to consider the path of the projectile after it has been launched. And gravity is the only external force on it. So, let's take a look at the simplest case of projectile motion. Now, the simplest case of projectile motion is just this. You have an object and you drop it. It has zero initial velocity, horizontal or vertical, and you're just dropping it and seeing how long it takes to hit the ground. So let's take a look at this first example here. So, for the first one, we know a couple of things. An object is dropped from a height of 3 meters. So this here is a distance that we have, our initial distance. How long does it take to hit the ground? Well, we're looking for a time here. We know that in projectile motion, we always have an acceleration due to gravity of negative 9.81 meters per second squared. In every projectile motion question, we are going to have a vertical acceleration of that, assuming the projectile is launched on Earth. We have an initial distance is 3 meters, and then we're looking for time here. So essentially what's happening is I have a projectile of some sort, it's a ball or another object, that's dropped, and it goes 3 meters down and hits the ground. And that's it. Now this is a question we've seen before in grade 11 physics when we're talking about free fall, and this is the simplest case of a projectile. So all I'm looking at is what is my time to go from here to there. So really straightforward. 1/2 AT squared. I can use this formula. I'm plugging things in. 3 equals 1/2 9.81 t squared. You may notice that I'm ignoring the negative sign here. The reason for that is because I happen to know that my time has to be positive. I can't have a negative time because that doesn't really make sense for us. So solving this out here for t, our time, is 0.78 seconds. So the time it takes the projectile to go from the top to hit the ground is 0.78 seconds. So this is a case for the first example here. We're just dropping something. Now, what I can do is I can actually look at this and go, is there another way that I could describe that? This here looks like something you've seen in math class before. And in fact, if I consider this a function of time, then this becomes a quadratic. So what I could do is let's say that I have distance as a function of time. And then I would have this as 1/2 acceleration times time squared. Great. However, I can also expand this to make this more interesting. So 1/2 AT squared, I need to include my initial distance in here. I'm going to go like that. So what I've got is I end up making a projectile motion parabola, because that's negative 9.81, and it looks something like this. It looks like a half of an inverted parabola. The peak here is at 3 meters, and this is time along this axis here. So I've got a parabola, and I can actually use that to solve things. If I find the zero of this parabola, where it crosses the x-axis, that will be 0.78 seconds. That's really useful because there's a lot of tools you can do with quadratics that apply to projectile motion. Right away, I'm going to say these only apply to projectile motion, the vertical component. The horizontal component we treat separately. The vertical component does follow exactly a parabola, which is useful. So here's starting off. This is the simplest case. Let's take a look at the next one that's slightly more complicated. So what if I take a ball and I throw it up with some velocity, and it goes all the way up to 3 meters here, and then returns back down to the ground? How long does this take? Well, interestingly, if I were to ignore the first half of this, we already solved the second half, and this was 0.78 seconds on the way down. What I do also know is that whenever I have a projectile motion, the time it takes to go up and the time it takes to return down to the same height, notice these are the same height, launch and land, this here is the same as this. So this time here is 0.78 seconds. This is an important property of projectile motion. Notice that my vertical up time is the same as my vertical down time. So for the second part, I can actually go my total time is my time up times 2. So I could go 0.78 times 2. So my t total is 1.56 seconds. So there's the total time to go up and come back down. Now, there are some important caveats, some important qualifications to this. So this is assuming launch and land at the same height. If I throw this off a building and it lands at a different height, lands on the ground, this will be different. If assuming we're launching and landing at the same height, my time is the same up and the same down. So if assuming launch and land at the same height, t up is equal to t down. That's useful. A couple other things. Right at the very top here, my vertical velocity is 0 at the top. So at the top of the path, my vertical velocity is 0, which actually makes sense. I'm going to come on over here for a second. And I'm going to go back and look at my quadratic here. If I add in the rest of this, the distance as a function of time is equal to 1/2 at squared plus my initial velocity times time plus my initial distance. If I start plugging this in, I end up getting a parabola, and for the second case, what this would look like is my parabola would look something like this, with an peak right here at 0.78 and 3 meters. So this here would be the vertex of my parabola, and if you notice, the slope right here is flat. So the slope of this parabola at the vertex is 0, and that means that my vertical velocity at the apex is 0. This quadratic here is one that's worth writing down. This is the complete quadratic function for a projectile, the vertical component. And I should actually indicate that that's the initial vertical, or the vertical distance, and that's the vertical velocity, and that's the initial vertical position. And that's... So this is the quadratic or vertical motion for a projectile. That's useful. We can use that a lot. However, there are also algebraic ways that we can solve this. I hope this has been a helpful video. We'll see you in the next one.